Good evening, our listeners, and welcome to today's class. Today, we'll be looking at the topic elementary probability. But before we continue in details with the study of elementary probability, it is also good that we look at the concept of set and set theory. The concept of sets and set theory. Concept of sets and set theory. Of course, we know that a set is a collection of well-defined objects that are enclosed within a set builder, or what we call braces. And traditionally, set is denoted with the uppercase of the letters of the alphabet, while the members that are contained within the set builder are enclosed or are represented with lowercase of the letters of the alphabet. Now, this set can be specified in two major ways, using what we call the roster method, or using what we call the rule method. Of course, in the roster method, what we do here is to completely enumerate all the members of a set. While in the rule method, we tend to use some signs in mathematics to write the members of the set in a very compressed or compact form. For instance, if we are talking about the roster method and one says, let a set A be a set that contains all the positive integers between 1 and 4 inclusive. The person is going to write that set A. It contains all the positive integers between 1 and 4 inclusive. So I'm going to have 1, I'm going to have 2, I'm going to have 3, I'm going to have 4. These are the members of this set, which are positive integers between 1 and 4 inclusive. It was possible for us to represent this set because the members of this set aren't many. It's just 1 to 4. What if we are talking about all the positive integers between 1 and 1,000 inclusive? We find it very difficult enumerating the members this way. So the roster method is not going to work very well here. Instead, we are going to use what we call the rule method. In the rule method, we are going to say, let that set be a set what? A. And that set A is a set of what? Of X. Such that we have that 1 is less than or equal to what? X, which is less than or equal to what? 1,000. What this means is that A is a set that contains members represented by X, such that X takes a value between 1 and 1,000 inclusive. So the moment we are given an information that this X is a positive integer that behaves in this manner, we must have communicated to whoever that is looking at this set A. So while this is a roster method, this is what we call a rule method. And most of the time in the pages of textbook, sets are always represented with the rule method. Then we talk about set theory. How does set theory equally come in here? Of course, set theory helps us now to study probability and random experiments, or what we call behaviors of random experiments. Of course, probability is the measure of the chance event has in occurring. And mathematically or expressionally, it is defined as the required outcome all over the total possible outcome. But then what do we mean when we say random experiment? An experiment is said to be random if and only if we cannot predict or tell the outcome of the experiment beforehand. That is actually what we call random experiments. For instance, some examples of random experiments are the toss of what? Of a die. When you toss a die up, a die has 6 faces. You cannot categorically be certain that 1 is the one that is going to come up, or 2 is the one that is going to come up down to 6. The only thing we know certain is that the number between 1 and 6 inclusive must come out, but we cannot be sure the particular number that is going to come out. So the toss of a die, which actually is an experiment, is random because we do not actually know the outcome of that experiment before performing it. Or consider the toss of what? Of a coin. When you flip a coin in the air and it falls on the floor, you cannot categorically say it's going to fall with the tail or it is going to fall with the head. These are what we call the random experiments. But before we go into detail in what we have, which is the elementary probability, we are going to look small at what we call the algebra of sets. And in this algebra of sets, we'll first of all begin by looking at different types of what sets and be able now to consider them one by one. So we are going to look at what we call types of sets. Types of what? Sets. Types of sets. We look at what we call types of sets. Types of sets. When we talk about types of sets, we might consider the following and look at them one by one. We have what we call singleton sets. Singleton sets. We equally have what we call subsets. What we call subsets. We equally have what we call proper subsets. Proper subsets. We equally have what we call improper subsets. Improper subsets. We have number 5. We also have what we call equal sets. Equal sets. We also have what we call power sets. Power sets. We equally have what we call null or empty sets. Null or empty sets. We equally have what we call union of sets. Union of sets. We equally have what we call intersection of sets. Intersection of sets. Then we have what we call, we have union of sets, we have intersection of sets, we have complement of sets. Complements of sets. Then we equally have what we call the universal sets. The universal sets. We are going to look at these sets one after the other. When do we say that a set is a singleton set? A set is said to be singleton if and only if that set contains only one member. That is, the cardinality of that set, which it stands to be, the number of members in that set is 1. For instance, if you have a set A and that set A is given as Ngozi, this set A contains only one person and that person is what? Ngozi. I equally have a set B and that set B contains something like 2 inside. These are what we call singleton sets because they contain only one member and the cardinality of each of them is 1. Cardinality is what we mean by number of members inside a set, and it is always written as what? N of capital A, meaning number of elements in this set A, which is equals what? 1. Ngozi. Or we talk about N of B, number of elements inside this B, which of course is equals what? 1. These are what we call singleton sets. What we call what? Singleton sets. Okay? Then we look at what we have looked at what we call the singleton set. We are going to look at what we call subsets. But when we talk about subset, we are going to talk about, consider two sets, A and B. Consider two sets, A and B. And let me say my A is defined as 1, 2, 3, 4, and 5. This is my set A. And my set B is defined as 1, 2, and 4. All the members of this set B are contained in this set what? A. Therefore, B is subset of what? Of A. Subset of A means that all the members that are in B, or all the elements that are in B, are contained in what? In A. And then instead, we are going to write it this way, that B is a subset of what? A. Implying that all the members in what? In B are contained in A. That is what we call subsets. But under this subset, we are having what we call proper subsets. And then we are having what we call improper subsets. For instance, if you come back here, we have looked at subsets in general. Let us now talk about what we call the proper subsets. When a set B are contained in A, and there are still other elements remaining in that what? A, we now call that B that it is a proper subset. That is to say that B are contained in A, but B is not equal to A. Look at the language here. What I'm now saying that for it to be a proper subset, proper what? Subset, we are going to say that B is a subset of what? A, but B is not equal to A. That is to say, is not equal to A. There are other members in A which are not contained in B. We call it proper subsets. Proper what? Subsets. However, when we have something like this, when I have B in this way, I had A to be 1, 2, 3, 4, 5, and B now become 1, 2, 3, 4, and 5. We are equally free to say, or we can equally say, that B is a subset of what? A. Simply because this B has element 1 to 5 inclusive, which are equally contained in what? In A. So B here is equally a subset of what? A. But B equals what? A. When it appears in this format, we call it improper subset. That B is improper subset simply because all the members of B are contained in A, but B on itself is equal to A. We call it improper subset. It was proper the other time because members of B were contained in A, but B wasn't equal to A. We call it proper subset. But in this case, we call it a improper subset. That's what we mean. This improper subset is going to be used to discuss. We have looked at proper subsets. We have looked at improper subsets. So we now come down to what we call equal sets. What we call what? Equal sets. Now, two sets A and B are said to be equal if and only if their members are equal. Their members are what? Equal. And there is difference between what we call equal sets and equivalent sets. For instance, A has members 1 to 5 inclusive. B has members 1 to 5 inclusive. Therefore, our A is equals B. Because look at my 1 here, look at 1 here, Look at 2 here, look at 2 here, look at 3 here, look at 3, 4 and 4, 5 and 5. So this is equal set. However, when we talk about equivalent set, we can have that my A equals 1, 2, 3, 4, 5. And I have a set B. A set B becoming what? 4, 9, 10, 11, and 12. We count. How many members are contained in A? 1, 2, 3, 4, 5. How many members are contained in B? 1, 2, 3, 4, 5. Therefore, my n of A equals 5 and my n of what? B equals 5. So when the cardinalities of two sets are equal, we call such sets equivalent sets. But they can only be equal if the cardinalities are equal and the individual members inside the set are also the same. That is what we call equal sets. So there is a difference between equal set and equivalent set. Equivalent set was not written down here, but on the course of trying to explain equal sets, we have also called it up and discussed. Then we come down to what we call a power set. And you permit me to clean this one, a power set. Okay? Of course, a power set of a set, say A, is a set that contains all the subset of A, including the empty set and the set A itself. I repeat, a power set A, for instance, or a power set of A, for instance, is another set that contains all the subset of A, including an empty set and the set A itself. For instance, look at a set A. Let me define. A set A is given like this. That set is a set of what? A, comma B. Okay? Then we are looking for all the possible subsets of this set A. So we are going to start with an empty set. So I have what we call an empty set, which is a null set, comma. There is a member here called A, so I will take that A. There is a member called B here, I will take that B. And then there is no other members here. And I have already taken A and I have already taken B. So the next I can consider is taking A and B at the same time. So I have another one, A, comma what? B. Okay? So if you want to write now the power set of what? Of A, power set, often written as what? Power set of A. It is given as, here is what? A set, empty set. So we now write what? Empty set this way. Then this is a set of what? A, you write what? A. This is B, you write what? B. This is what? AB, you write A, comma what? B. Then you close the brackets. This is actually what we call a power set. And it is always represented, or the formula is always given as 2 raised to power n, where this n is the number of elements that are contained in this set. For instance, the number of elements contained here is 1, 2. And then I have that here now becomes 2. And 2 raised to power 2 is what? 4. So we now come down to this power of set to count the number of elements we have inside there. So, or the number of subsets I have there, I have 1, 2, 3, 4, which is exactly the same as 2 raised to power 2. So this is actually what we call a power set. Let me expand the member of A and we look at it also. So permit me to equally clean here. So when we come down here, then I might increase the members of A. I have A, comma B, comma C. Then we are to write the power set of this A. Then we now come. The power set of that A becomes. First of all, we are going to start with an empty set. So I'll open, I'll write empty set, I'll close. Then the first element here is what? A. I will take it. The second one is what? B. I will take B. The third one is what? C. I will take C. I'm done taking all the members in A in their single nature. So I now think about taking twos in one. So I'll now open. I'll take AB, A comma B, comma. I'll open. I'll take A and C, A comma C. Then I'll now take B, C. I'll open and take what? B, comma C. I'll close the brackets. Then we are equally now, we are done taking two in one. So the only one that is left now is taking 3 at a time. So we open and take A, comma B, comma C, and close and close. So we now count. This thing is 2 raised to power what? 3. Because I have 1, 2, 3. And this equally becomes 8. And we count 1, 2, 3, 4, 5, 6, 7, 8. This is what we call power set. It can be given up to 4 members here, and you are told to generate the power set, or they can give you a set A and ask you, find the cardinality of the power of the set of A. So you are first of all to enumerate all the possible subsets of that A and be able to count the sets that are inside. So that's what we mean by power sets. And I want to believe that it is clear with everyone. Power of sets. So I'll clean this. Then we go over to what we call the null or empty set. A set is said to be null or empty if that set does not contain any elements. So in that case, you are going to have a set A, and that set A will just have a set builder this way. This is what we call an empty set. Another way of writing an empty set is to write that A equals, you write like this. This is also what we call an empty set. It's always called null set. If you don't call it empty set, you call it a null set. And I want to make this thing clear that each time they write something, a set A equals, and they put 0 inside, it is no longer an empty set because this set A contains 0 inside. Our interest is, let there be nothing inside, whether that thing is 0 or not. So the cardinality of this one here that contains 0 is 1 because it has a member, that member is what is 0. But this one, it doesn't have a member, and this one, it doesn't have a member. Therefore, the cardinality of an empty set is 0. They can ask you that question anywhere. The cardinality of an empty set is 0. It doesn't have any member inside. That's actually what they call null or empty sets, either written this way or written this way, which are different from the one that contains 0 here. We call it a null set. Then we go down together to what we call union of sets. What we call what? Union of what? Sets. Now, when you talk about a union of two sets, say A or B, you are talking about a set that combines all the elements of the set A and B without repetition of numbers. That is what we call a union. And the union can go beyond two sets. You can talk about the union of the sets A and B and C to any particular number of what sets, any finite number of what of sets. You are talking about combining all the members of those sets mentioned without repeating numbers. For instance, let us consider, for the sake of this class, a set A and B defined this way. So I have a set A, and that set A is defined as 1, 2, 3, 4. And I have a set B, and that set B is defined as what? We have 2, we have 4, we have 9, and we have 10. So we are to find the union of sets A and B. And it is written like this. We have what we call A union B. That is how it is written. This equals. We are going to combine all the elements in A and B, but we should be careful not to repeat a number that has occurred. So first of all, let us exhaust A. We have 1, we have 2, we have 3, we have 4. We are done with A. We come down to this one. We are to pick 2 from B, but 2 has occurred. So we are not going to pick it. We come to 4. We could have taken 4, but 4 has occurred here. We come here to 9. 9 has not occurred here, we pick 9, and 10 has not occurred here, we pick 10. This is what we call union of sets. A set that contains all the members in A and B without repetition of numbers or elements. Then we now move down to what we call intersection of sets. Intersection of what? Sets. An intersection of a set is a set that contains all the members that are common to both set A and B. You might be looking at set beyond 2. You are just interested in looking at the numbers or members that are found in all these sets that are mentioned, and they become what we call intersection of sets. For instance, when we are still looking at what A and B, it is always written as what? A intersection what? B. This is equals. We come down here. There is 1 here in A, there is no 1 here, so it will not be taken. There is 2 here, there is 2 here, so they have 2 in common. I will pick 2, comma. There is 3 here, there is no 3 here, it will not be taken. There is 4 here, there is 4 here, it will be taken. Then I will take 4. So this is an intersection set, which is a set that contains all the members that are common to A and B. So it is called an intersection of sets. Okay? And then there is another thing I want to say. I could have enumerated it here. We have what we call disjointed sets. Disjointed sets. 2 sets A and B are said to be disjointed if their intersection is empty. We call it a disjointed set. For instance, let me write something like this. I have a set A defined this way, and I have a set B defined this way. As 6, 7, 8, and 10. This is what I have. Then we now go and look for A intersection what? B. So we have A intersection what? B equals, we open a bracket. 1 is here, no 1. 2 is here, no 2. 3 is here, no 3. 4 is here, no 4. So it is an empty set. And on that note, we say that A and B are disjointed sets. That is, they do not have any member sharing in common. It is called disjointed sets. Okay? Then we go down to what we call complement of a set. Before we talk about this complement of set, it is possible or better we talk about what we call the universal sets. An universal set is a set that contains all the possible outcome of a trial or all the possible elements that are under consideration. So we can define an universal set to be a set that contains either positive integers from 1 to 10. For instance, I have universal set. It can be written as like this as an universal set. It can equally be written as like this as an universal set. It can equally be written as omega as an universal set. So you might see any of these things representing universal sets. So let me take maybe this very one here. I have this equals set of integers from 1 to 10. So I have what? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This is what I have. Then I have another set A, and that another set A is a set that contains something like 1, 3, 9, 10. When we talk about the complement of set A, we are talking about all other members that are contained in universal set, which are not contained in this set A. We call it a complement. And when we want to write a complement, it can either be written like this, A complement, or it can be written as what? A complement. Any of these is acceptable. A complement or A complement. We are now going to see is a set that is going to contain all the elements here, which are not here. 1 is here, 1 is here, we will not pick it. 2 is here, but 2 is not here, we pick 2. 3 is here, 3 is here, we will not pick it. 4 is here, but 4 is not here, we pick 4. 5 is not here, we pick 5. 6 is not here, we pick 6. 7 is not here, we pick 7. 8 is not here, we pick 8, and we close it. So these are what we call a complement or complement of A. All elements contained in the universal set which are not contained in that subset under discussion. Okay? Then we now go down to, yes, we have looked at what we call the universal set. We have looked at what we call complement of sets. These are a few of the things we just feel is necessary that we provide ourselves with before we begin to discuss elementary probability. And another thing that is going to help us to discuss elementary probability very well is two concepts which we call permutation and combination. So permit me to clean here. We are going somewhere gradually. Going somewhere gradually. I say it's what we call permutation and combination. What we call permutation, and combination. Yes. Permutation, of course, is the number of ways of arranging R objects out of N objects. Number of ways of arranging R objects out of N objects. This R is always less than or equal to N, and it is always written like this. This is what? N permutation what? R. Or arranging R objects out of N objects. And it is expressed as N factorial all over N minus R all factorial. This is how to express it. So somebody might say, in how many ways can we arrange two letters of the word book, for instance? In how many ways can we arrange two letters of the word book? First of all, we write the book. The book is written like this, B-O-O-K. We count. How many words are in this book? 1, 2, 3, 4. So we have that N equals what? 4. But we're interested in arranging two letters out of this 4. So my R is equals what? 2. Then I will return back here. Wherever place I see N, I will put 4. And wherever place I see R, I will put 2. And this thing becomes that my 4 permutation what? 2 is given as 4 factorial all over. We have 4 minus 2 all factorial, which is equals 4 factorial all over. 4 minus 2 is 2, and I have factorial outside, 2 factorial. Then we express this. That this equals 4 times 3 times 2 factorial all over. Here is 2 factorial. So that these 2 factorial will cancel these 2 factorial. And what I have left is 4 times 3, which is what? 12 ways. So we can arrange 2 letters of the word book in 12 ways. That is what we call permutation. Or you can equally say, in how many ways can we arrange 4 persons on a seat given that it is only 2 spaces that are available? Or arranging 4 persons in a seat given that we have only 2 possible vacancies where they can sit down. In that case, we still talk about how many persons are involved here, or let me use in how many ways we can arrange 3 persons in a seat that has only 2 vacancies or only 2 spaces. I say, how many persons are we talking about here? We are talking about 3 persons. 3 persons. So my n equals what? 3. How many spaces are available for us there to arrange these people? Only 2 spaces. So I have that. I have 2 spaces. So my r equals what? 2. So in that case, I'm going to have what? Instead of writing now, I'll come here. My n becomes what? 3. I have 3 permutation. My n becomes what? 2. This is equals to 3 factorial all over. Open a bracket. 3 minus 2 all factorial. This is equals. I have what? 3 factorial all over. 3 minus 2 is what? 1 factorial. And 1 factorial is what? 1. So we just come and say this is 3 times 2 times 1. That is expressing this 3 factorial. And this becomes 3 times 2 is what? 6 times. This is 6 ways. So we can arrange, 3 persons on a seat, given 2 available spaces or chances on that particular seat for them to sit down. These are what we call permutation. Or somebody can equally ask you, in how many ways can we arrange 4 persons in a seat, given that we have 4 available space? We call it arrangement of 4 items, taking 4 at a time. Taking 4 at what? A time. And in that case, what I have here becomes, permit me to clean here. In that case, what I have here becomes, I have 4 persons that we are going to arrange, and then we have 4 spaces. So we have what? 4 permutation 4. This becomes what? 4 factorial all over 4 minus 4 all factorial. This equals 4 factorial all over 0 factorial. And we must note that 0 factorial is 1. So 0 factorial equals 1 factorial equals 1. So in that case, this 4 factorial divided by 1 will return 4 factorial. And then that 4 factorial equals 4 times 3 times 2 times 1. 4 times 3 times 2 times 1. 4 times 3 is what? 12. Times what? 2 is 24. Times 1 is 24. So we have 24 ways in arranging. So that is similar question you can see about arranging 4 books in a shelf, taking 4 at a time. Arranging this, taking that at a time. That's actually what we call permutation. Then we come down to what we call combination. In the combination, we are talking about the number of ways we can select some persons out of the whole persons. That is, number of ways of selecting R objects out of N objects. And it is always written like this for combination. It is always written like this. That is N combination R. Number of ways of selecting R objects out of N objects. And this my R must be less than or equal to N. That is a condition. So in that case, it is always expressed as that my N combination R is given as N factorial all over R factorial into N minus R all factorial. This is how to express it. So they can be giving you questions like, in a class of 5 persons, In how many ways can we select 3 persons to represent the class? A class of 5 wanting to select 3 persons to go and represent the class. So first of all, you ask yourself a question. You ask yourself a question. Okay, so how many persons are in that class? There are 5 persons there in a class. And out of these 5 persons, of course, my n now becomes what? 5. We are meant to select the 3 persons who are going to represent the class. So, which means I have that my R equals what? 3. Selecting 3 persons. So, in that case, what I have now becomes what? In place of n, it becomes 5, and in place of R, it becomes 3. So, this equals what? I have what? 5 factorial for this all over. Here becomes my what? 3 factorial into. Inside here becomes what? 5 minus 3 all factorial. This equals 5 factorial all over. Here is what? 3 factorial into. This is, or let me say multiply by 5 minus 3 is what? 2 factorial. And this thing can be expressed as this. This is 5. 5 times 4 times 3 factorial all over. Here is what? 3 factorial multiplied by 2 factorial means 2 times 1, which becomes what? 2. Okay? So 3 factorial is here, 3 factorial is here. This and this will cancel. So there is 2 here, there is 4. 2 here, 1. 2 here is 2. 5 times 2, we have 10 ways of selecting 3 persons from a class of 5 persons. There are always other questions they ask this way. They can tell you in a class of 5, in how many ways are we going to select 3 persons to represent the class? Given that one particular person must be included there. One particular person must be included in that group of 3. So in that case, it is not your duty to select the person that must be included. It's already known and established that the person must be included there. So you now return back. When one person is going to be included in the class, is as good as must be included in the group, it's as good as I ask the person, stand up, go the other side, you're already included. Then you are now left with what? 4 persons remaining. And remember that you are going to select 3, and the other person has gone there to stay, who must be there. So you are now left to select what? 2 persons that is going to join them. And you are now selecting that 2 out of 4 persons. You see how this question is. So at times you see them write it this way. Let me show you. At times you see them write it this way. At times you see them write it this way. You see them write it this way. One person must be there. So you come to the class, remove that person. The number you are going to select, you remove that person. And they will always write n minus 1, combination r minus 1. Where this my n is what? Is 5. And this thing becomes what? 5 minus 1, combination. My r is what? 3. You have 3 minus 1. This thing becomes what? 5 minus what is 4, combination. 3 minus 1 is what? 2. You are now selecting 2 out of 4, which invariably becomes what? 4 factorial all over 2 factorial into, we have 4 minus what? 2 all factorial, which becomes what? 4 factorial all over. Here is what? 2 factorial multiplied by 4 minus 2 is 2 factorial. This is equals to 4 times 3 times 2 factorial all over 2 factorial times, because 2 factorial is of course 2, so I can easily write 2. 2 factorial will go into 2 factorial. This thing is 1, and this is what? 2. And 2 times this will equally give us 6 ways of doing that. So we have 6 ways of doing this one, when we must include one particular person in that group. There are other questions they ask this way. They give you a condition that these 5 girls here, or 5 persons here, must be made up of what? Boys and girls. So they can come and say that out of these 5, 3 are boys. So permit me to write that out of this we have three boys, and then we have two girls. So, and we are meant to select three persons who are going to represent the class that is made up of what? Three boys and two girls. They might give us a condition. The condition is select select two boys and select one girl. Select two boys and select one girl. So in that case, you approach the question this way. You approach the question this way. Okay? You approach it this way. So in that case, what you have now, you are to select two boys out of three boys. So you have what? 3 combination what? 2. And in mathematics means multiplication, multiply by. You are to select one from two girls. So you have 2 combination 1. Selecting 2 here and selecting 1 will make up that 3 that is going to represent that class. Okay? In that case, how it is now going to be is now 3 factorial all over. Here is 2 factorial into 3 minus 2 all factorial times 2 factorial all over. Here is what? 1 factorial into 2 minus 1 factorial, which becomes 3 factorial all over. Here is what? 2 factorial times 3 minus 2 is what? 1 factorial. So multiply by 2 factorial all over. This is 1 factorial times 2 minus 1 is what? 1 factorial. 1 factorial times 1 factorial is just like 1 times 1, which is 1. Then here, I am going to express this to be what? 3 times 2 factorial all over what? 2 factorial. Because 2 factorial times 1 factorial is just like 2 factorial. Then here is 1 factorial times 1, which is 1. 1 divided by this is which means multiply by 2 factorial. So these 2 factorial will cancel these 2 factorial. I am left with what? 3, isn't it? So, and here I am left with what? 2. So this thing becomes 6 ways. We can actually select 2 boys and select 1 girl to go and represent the class. They gave a condition this particular place. Okay? So this is actually what we are talking about in combinations and the rest of them, where they give you a question and you are to find either the number of ways of what? Selection, or the number of the ways of arrangement in terms of permutation and in terms of combination. We want to believe that you have not been so confused with what we are saying. Okay? So we are now going to move into what we call sample space and event space. What we call what? Sample space and event space. Sample space. Sample space. And what we call event space. Event space. Event space. When we talk about a sample space, we are referring it to be a set. And it's one of the reasons why we had to earlier on look at the concept of a set. We say that a sample space is a set that contains all the possible outcomes of an experiment or a trial. For instance, when you get a die, or when you get a die and you cast the die up, you have 1 to 6 faces of a die. Therefore, 1 up to 6 inclusive has the chance of going to occur. So if you have a set like this, a set S, we normally write it as S, as sample space, that contains 1, 2, 3, 4, 5, and 6. This is a sample space of a throw of a die, because all the possible outcomes that one can get when one flips up that coin, flip up that die, has been contained in this S, 1 to 6. So we call it a sample space. Then if you are talking about something like maybe you are tossing what, or if you have now 2 coins this time around, you have 2 coins, 2 dice. In the two dies, of course, you are going to prepare a table. How to prepare the table is you are going to have what we call die 1 and have what they call die 2. Then you have a line this way, you have a line this way. Of course, this die 1 contains 1, 2, 3, 4, 5, 6. This die 2 contains 1, 2, 3, 4, 5, and 6. So the implication that here you can carry the two dice, you throw them up, one will appear in the other die, and one will appear in the other die. So it is a possibility, and you have 1, 1. You can equally throw it up. You have you have 2. You have 1 occurring from die 1, from die 2, and you have 2 occurring from die 1. So you now have what we call 1, 2. Then here becomes 1, 3. Here is 1, 4. Just pick the value for the row and pick any of the column. Then you have what? 1, 5, 1, 6. Then when we come here, what we are now going to have here is what? This is 2, 1. Here is what? 3, 1. Here is what? 4, 1. Here is what? 5, 1. Here is what? 6, 1. So if you count, you have 1, 2, 3, 4, 5, 6. And you have 1, 2, 3, 4, 5, 6 as the column heads and then the row heads. And 6 times 6 is 36. So when two dice are flipped up together, you have 36 possible outcomes that is going to come out there. A set that collects all these 36 possible outcomes is what we call a sample space. What we call what? A sample space. I want to believe that you did not have a problem understanding what we call a sample space. So permit me to clean this particular thing. However, when we talk about event space, of course, event is just a subset of the sample space. You understand? Event space is a subset of the sample space. It's a collection of defined members of the sample space. For instance, when we cast or when we threw up a die, we had these as the possible outcome of that trial, which we call the sample space. I can define another set A that is going to be a set of odd numbers that cannot be divided by 2. And in that case, I have 1, it cannot be divided by 2. 3, it cannot be divided by 2. 5, it cannot be divided by 2 without a remainder. So here I am talking about odd number. Then I have a set what? B, that is going to be a set of even numbers. Those that are going to be divided by 2 without a remainder. Of course, 2 will be there, 4 will be there, and 6 will be there. So here is what we call even number. Now this set A is an event because its members are contained in this sample space. And then this event B is equally what? This B is also an event of the sample space because all the members contained in this B are in the sample space. That's what we call the sample space and then the event space. And we have different kinds of events. We have different kinds of what? Events. We have what we call elementary events. Elementary events, or what we call single events. Elementary events. Elementary events, or what we call a single event. We have equally what we call compound events. Compound events, otherwise called mixed events. Mixed events. We have what we call equally likely events. Equal likely events. Okay? We have what we call mutually, or let me say, we have what we call exhaustive events. Exhaustive events. Then we have what we call mutually exclusive events. Mutually exclusive events. We have what we call independent events. Independent events. There are other kinds of events that people can talk about, but let us look at these ones closely. An event is said to be elementary or single if it contains only one element, just like when we defined a singleton set. So, elementary event is for the event as singleton set is for the set. It contains only one member. It can be when you throw this thing up, you talk about a set A that contains the highest number that one can obtain when you cast a die. The highest number you can obtain is what? 6. So it is going to contain 6. And if it contains only 6, you talk about elementary events. Then we now talk about what we call compound events. In the compound event, we are saying that the event contains more than one member or element. For instance, this my A, which is a set of odd number, is a compound event. It contains more than one member. Same thing applies with what B is a compound event. Then we now talk about equal likely or equally likely events. Let me use equally here. Equally likely events. Two events are said to be equally likely if the occurrence of one cannot suppress the occurrence of the other one. So they have equal chance of occurrence. For instance, when you get a coin and you flip the coin up, the head has the same chance of occurring as the tail has, as long as the coin is not biased. The same thing applies with what? A die. When you cast a die up, one has the same chance of occurring to 2, the same to 3, the same to 4, down to 6. They are called equally likely events. Occurrence of the other one can cheat or reduce the chance of occurring of the other one. You understand? So they have equal probability of occurring. That's exactly what we mean. So we now talk about exhaustive event. In exhaustive event, this is just very close to what we call the sample space. You understand? For instance, if you have a sample space here of a throw of a die having members 1 to 6, and you define another event that is the collection of all the integers between 1 and 6, you find out that you end up going to write this thing again. And by that, you have exhausted all the members in the sample space. And that event you define that way is called the exhaustive events. Then we now come to what we call mutually exclusive events. Two events A and B are said to be mutually exclusive if the occurrence of A will make B not to occur. Occurrence of one stops the other one from occurring. That is what we call mutually exclusive event. And if we have a mutually exclusive event, an occurrence of one will make the other one not to occur, it means that the intersection between the two sets A and B is an empty set. For instance, if you pick up a coin and you throw a coin up and that coin falls with what? A head. It means that tail cannot occur again. So occurrence of that head has stopped the tail from what? Occurring. Such things are called a mutually exclusive events. Then we now come to independent events. In independent event, of course, two sets A and B are said to be independent if the occurrence of one does not affect the occurrence of the other one. If you have two coins in your hands and you want to flip two of them, and you flip them up and they fall, if head has occurred in coin A, it cannot stop tail from occurring in coin B. So in that case, the set is not empty. The set is not what? Empty in that case. So we are going to give the set notation of mutually exclusive event and then of independent events. Permit me to clean this side. So if set A and B, if A and B are mutually exclusive, if they are what? Mutually exclusive, it implies that their union, A union B, equals A plus B. This is true for this set. The union is just A plus B. And if these A and B are mutually exclusive, it means that A intersection what? B equals an empty set. We earlier had mentioned it. Becomes an empty set. This is true for this. But if sets A and B are independent events, it implies that A union B is given as A plus B minus A intersection what? B. And A intersection what? B is not empty. It's not an empty set. These things are true. These things are very true. So this symbol or this illustration for mutually exclusive and then this illustration for independent event. So when you are told probability of A or B occurring, it is just probability of A plus probability of B in terms of mutually exclusive. And probability of their intersection is equals 0 because there is nothing inside it. But when we come here and they ask you for the probability of A or B, which means A union B, is going to be probability of A plus probability of B minus probability of A intersection B. That's what it becomes there. For instance, let us pick little thing and show illustration of what we have said about mutually exclusive and then independent event. Let me clean this. Let me say that I threw my die and I am going to use S as sample space to collect all the possible outcomes. It means that my S is given as this: 1, 2, 3, 4, 5, and 6. It's what we have. So in that case, I can define a set A that is going to be a set of odd numbers, like I did before: 1, 3, and 5. I define a set B that is going to be a set of even numbers, which is 2, 4, and 6. Okay? Now, when we talk about their intersection here, we find out that A intersection B equals, that is, all the elements that are found in A which are equally found in B. Here is 1, no 1 here. Here is 3, no 3 here. Here is 5, no 5 here. So they don't share any element in common. Which means this actually is going to be an empty set. And the probability of this empty set is going to give me 0. Which means probability of A intersection what? B is going to be what? 0. But we now have that A union B equals. A union B means the combination of all the elements in A and B without replication of numbers. So we consider the A first. So I have what? This is I have a, remember, yes, that we said that this is given as A plus what? B. So we are going to combine all the elements that are found in A and B, and this thing becomes a set of, here let us exhaust this, 1, comma what? 3, comma 5, comma here we are 2, 4, and 6. And this thing becomes their union. Okay? Are we there? Then there is something we want to look at in the probability. Now, probability is defined as the required outcome all over total possible outcome. Which means if I come, I will say that probability equals total possible outcome means all the elements that are contained in this sample space. Which means I'm talking about what? N of S all over N of what? A. If I'm looking for probability of event A occurring, we have N of what? A. So in that case, I'm talking about probability of event A occurring. So this is going to be bullshits. Sorry for that exclamation. So we have that here is what? A, and here is what? S. That is the number of elements in that event A all over the number of elements in that sample space S. The number of elements in event A is what? 1, 2, 3. So I have what? 3 all over. The number of elements in this one is what? 6. I have all over 6. Which means 3 here is what? 1, and 3 here is what? 2. So I have 1 over 2. The same thing applies in event B. P of event B is given as what? N of what? B all over what? N of S. This becomes 1, 2, 3. It is still what? 3 over 6, which equals 1 over what? 2. So I'm interested in looking at the probability. I'm interested in looking at the probability of A union B. Probability of A union B. If you talk about the probability of A union B, which I have stated in a mutually exclusive event, which we saw here, because A intersection B is empty. So we have that the P of A union B equals P of A plus P of B, which is equals P of A is 1 over 2, so I have 1 over what? 2 plus P of B is 1 over 2, 1 over 2, which becomes 1. Because 1 over 2 plus 1 over 2 is 1. Because we have considered this A and B contains every possible thing inside here. So in as much as this is an empty set, the probability of 2 of them must definitely give us 1. So this thing happens when we talk about mutually exclusive events. So let us now do another illustration that is talking about the independent events. Talking about the independent events. Let me now define a set A. Let me define a set A, which is a set of what? X, such that I have that 1 less than or equal to X less than or equal to 4. This is my set X, set A. So if that is set A equals, I'll open a bracket. X takes a value from 1 to 4 inclusive. So I'm going to have 1, 2, 3, 4. I'll close this. Then I have a set B that is going to be defined by. I have what? Y such that I have that this is a 3 less than or equal to what? Y less than or equal to, let me say, less than or equal to 6. This is what I have. Or let me say less than or equal to 4. Less than or equal to 4. Permit me to use 5. I'm generating these questions of hearts. Okay? So in that case, of course, my B equals is going to be, of course, it takes a value from 1 to 5, from 3 to 5 inclusive. So I have 3, I have 4, I have 5. This is my A, this is my B. Okay? So we are going to look for the probability of A occurring and look for probability of B occurring, first of all. Probability of A occurring means, or before we do that, we say that my A intersection B equals. We look for something that is common here, that is common here. There is 3 here. There is 3 here. There is 4 here. There is 4 here. So they share 3, 4. So now if I want to talk about the probability of what A, I will say P of what A is given as N of A all over N of what S, which equals. N of A means 1, 2, 3, 4. So I have 4 all over 6, which is what? 2 all over 3. Then I talk about B. So I have that P of what? B occurring is N of B all over N of S. This equals 1, 2, 3. So I have 3 all over 6, which is equals 1 over 2. Because here is 1 and here is this. Recall that our intersection is not empty. So we are going to look for probability of the intersection. And the probability of the intersection is going to be, we have that the probability of A intersection B is given as N of what? A intersection B all over N of S. This equals. Number of elements in A intersection B is 1, 2. So I have 2 all over 6, which is 1 over 3. So the probability of A intersection B occurring is 1 over 3. Unlike before, that the probability of A intersection B was 0. So finding the probability of A, event A or B occurring here becomes P of A union B equals P of A plus P of B minus P of A intersection B. So this equals P of A occurring is what? 2 over 3. So I have 2 over 3 plus. P of B occurring is 1 over 2. I have 1 over what? 2 minus. P of A intersection B occurring is what? 1 over 3. So this is equal. We can take LCM of this and this, which is 6, and write 6 here. So in that case, we are going to say 6 divided by 3 is what? 2. 2 times 2 is what? 4 plus. 6 divided by 2 is what? 3. 3 times 1 is what? 3 minus. We have 6 divided by 3, 2. 2 times 1 is what? 2. This is equals. 4 plus this is 7. 7 minus 2 is what? 5. So we have 5 over 6 in this context. And the other time when we solved, we had a 1 when we looked when it was mutually exclusive effects. This is 5 over 6. This is actually what we are talking about, mutually exclusive events with their probabilities. We equally want to believe that you may have understood what we are saying here. So permit me to clean the board so we can go into something we have again. Okay, we are equally going to look at another concept which we call random variables. Which we call what? Random variables. Call it random variables. My light has gone off. Thank you. We continue next time.